Hello everyone, my name is Vincent Ledvina, and today I will be showcasing the North Dakota Dual Aurora Camera Project, an exciting new tool for Aurora chasers and scientists, helping to answer important science questions about how the Aurora behaves at mid-latitudes, serving as a platform for citizen science through Aurorasaurus, and existing as an easy-access community resource for the public to view the Northern Lights from North Dakota. First, a little bit about myself. I'm a senior physics undergraduate at the University of North Dakota, and I have been interested in photography since around the age of 16 and love the outdoors. I captured my first Aurora when I was 17 years old, which you can see at the bottom right, and the rest was history. The first Aurora I captured was only because of citizen science reports in my area on the Aurorasaurus platform, and public resources like Aurora cameras and social media groups have helped me through the years with tracking the Aurora and answering the all-important question of, is it visible from my location? So with that out of the way, let's now talk about the Aurora in a general sense, because it's important to have some background before delving into the specifics of NoDDAC. The Aurora is created from the interaction of the solar wind with Earth's magnetic shield, and through various processes, primarily through magnetic reconnection, solar wind particles are streamed along Earth's magnetic field lines to the polar caps, where they are deposited into the ionosphere, which is Earth's outer atmosphere. In the ionosphere, electrons from the solar wind ionize gas, emitting photons in the process which we perceive as the Aurora. The color of the Aurora depends on the height and composition of the gas being ionized, with the green Aurora you see here being the result of oxygen emission between around 100 and 200 kilometers. As I stated earlier, the Aurora manifests in what are known as auroral ovals, which form over the north and south magnetic poles. When auroral activity increases, which can happen during geomagnetic storms, the auroral ovals may expand equatorward from high latitudes to mid-latitudes, allowing the lights to be seen from various places like the US and southern Canada. To track the Aurora, while solar wind data and indexes like the AE, AU, and KP are all fine, to an extent they are just a proxy for auroral strength, and having physical cameras imaging the night sky is really the best way to gauge what the Aurora is actually doing. Furthermore, Aurora cameras can provide useful data to scientists who study the Aurora, since they are often time and color calibrated and offer a consistent view that can be correlated to other data like solar wind or magnetometers. With the growing number of Aurora citizen scientists, Aurora cameras can also be used to spot rare auroral features or phenomenon like Steve, and can be cross-referenced to ground reporters to build a database of observations. While there are a plethora of Aurora cameras in high latitude regions, including NASA's Themis network, which is shown here in this visualization, there are very few science-grade Aurora cameras with mid-latitude coverage, which was the motivation for the NoDDAC project. Situated at Martin's Observatory, a facility owned and operated by UND's Department of Physics and Astrophysics, NoDDAC provides a crucial mid-latitude perspective of the Aurora with one main advantage. There are two cameras. With a north-facing video camera and an all-sky stills camera, NoDDAC can provide the public with an invaluable resource to monitor cloud cover and aurora conditions, while also providing scientists with a short timescale picture of the Aurora and an all-sky view of the Aurora at the same time, which is helpful for large events where the Aurora can be seen across the entire sky, and for studying phenomena that move quickly, like Steve, which benefit from the shorter exposures of NoDDAC's north-facing video camera. NoDDAC is a partnership between multiple organizations. This allows us to create a dual resource that benefits scientists and the public. The University of North Dakota was instrumental in providing funding and a space to house NoDDAC. As mentioned earlier, NoDDAC is situated at Martin's Observatory, a facility around 45 minutes northwest of the main campus. Besides being under Bortle 2 skies with minimal light pollution, the observatory also has access to high-speed internet and reliable power, which make running a full-time project like this possible. Aurorasaurus was influential in providing oversight for the project, and NoDDAC also incorporates Aurorasaurus citizen science. If Aurora is detected on the north-facing camera, a tweet is sent out with an image of the display, which can be used by Aurorasaurus's Twitter algorithm to display a positive Aurora sighting report on their auroral oval map. The Live Aurora Network is a commercial Aurora live streaming service with Aurora cameras around the world. They partnered with this project and provided the enclosures, supporting hardware and software that runs the cameras. Without Live Aurora Network's partnership, NoDDAC would not exist. The tandem of the all-sky imager and the north-facing video camera is really what makes NoDDAC special. The all-sky imager on NoDDAC consists of a Canon T6 camera and a Sigma 4.5mm f2.8 fisheye lens. The setup captures a large field of view of the sky around 140 degrees. From 1 hour after sunset to 1 hour before sunrise, the camera takes exposures at 30 seconds, f2.8, and variable ISO. The ISO varies based on the lighting conditions, so during a full moon night or during bright aurora, the ISO is lower than during darker conditions to keep the same image brightness. The camera captures images with a cadence of 2 minutes in JPEG format and uploads them to a web server that can be accessed from any web browser. The all-sky camera is helpful for the main reason that during large auroral displays, you may see aurora overhead and to the south, which would be outside the field of view of the north-facing camera. The all-sky imager ensures that the entire aurora display can be analyzed. NoDDAC also contains a north-facing camera consisting of a Sony a7S II camera with a Sony 24mm f1.4 GM lens. This setup produces an 84-degree field of view of the northern sky, which is streamed to the Live Aurora Network's platform as well as YouTube, under the NoDDAC YouTube channel. The settings for the video are a constant aperture of f1.4 and shutter speed of 1/4 of a second, with the ISO able to vary based on available light. The Sony a7S II is a state-of-the-art camera with a full-frame sensor and extremely low noise at high ISOs, and is used by the Live Aurora Network and their Aurora cameras, as well as by countless Aurora photographers to capture real-time video of the lights, so it was a natural fit for NoDDAC. NoDDAC has been operational for about 1 year and has already seen great success in providing useful data for possible scientific investigation. Here is one example of a Steve captured on March 13, 2021 by the NoDDAC All-Sky Imager. It should be noted that this was captured before we upgraded the lens from a Rokinon 8mm f2.8 to the current Sigma 4.5mm f2.8. I was also capturing images at the same time as NoDDAC with 2 of my own cameras, and I synced up 3 different views of the same Steve arc at 3 separate times, and you can see how these views could be used for triangulating the height of the structure and studying how the small-scale picket fence feature evolves from different vantage points. Studying Steves and other rare phenomena is one of the main goals of NoDDAC, and if this particular Steve were captured on the north-facing camera as well, then we could triangulate the height of the structure just with NoDDAC. So by having 2 cameras, each with its own field of view, you can essentially get 2 perspectives, which is very powerful. Next, I would like to highlight a particularly active night of aurora on October 11th, 2021. On October 9th, there was a full halo CME associated with an M1 flare, and over the course of just about 2 days, it traversed interplanetary space and collided with our planet. The result was a G2 geomagnetic storm that produced auroras in North Dakota that were seen on NoDDAC. Each night, NoDDAC not only live streams video, but it also records still images from both cameras and compiles them into time lapses in the morning. The time lapses and stills are all stored on a publicly accessible FTP server, and here you are seeing the software-generated time lapse from the north-facing and the all-sky cameras. Strangely enough, the north-facing camera became defocused partway through the night, which was odd, but since the aurora doesn't really have any definition to begin with, it wasn't a major issue. Besides normal auroral precipitation being recorded on NoDDAC, the cameras also saw a Steve event, possible auroral dunes formation, and a type of SAR arc. Many of these features are still not entirely identified, and NoDDAC images could be useful to scientists who want to examine these events more closely in conjunction with other field reporters' images. One of the applications we want to explore with NoDDAC is how certain physical parameters like the BZ component of solar wind is correlated with visual auroral activity. It is already well known that negative BZ values lead to better reconnection of the solar wind with Earth's magnetic field lines, transferring more of the solar wind's energy into visible aurora. Overlaying the night of October 11th with solar wind data from Discover, we can correlate periods of negative BZ with intense auroral activity, verifying this theory. This is helpful for scientists to understand how the aurora responds to changes in the solar wind during larger geomagnetic storms, and it's a useful tool for the public since it directly shows the influence of negative BZ on aurora. Also note that this is not time-corrected data, so you will see an inherent lag from when the data is sampled at L1 and when it is geo-effective at Earth. The most intense aurora seen from the cameras was on the night of November 3rd, 2021, where the effects of a series of CMEs fired from the sun just days before created G3 strong storm conditions, with aurora viewing as far south as Joshua Tree, California. NoDDAC observed dusk to dawn aurora as well as overhead coronas, as it was inside the auroral oval at the time. It also observed intense pulsations of purple aurora during the pre-dawn hours on November 4th, which was very unusual. Strong geomagnetic storms often produce strange and anomalous types of auroras or subaraural phenomenon like Steve, so this data captured by NoDDAC will be valuable to scientists as we reconstruct the events on November 3rd and 4th. This storm in particular is a great example of why having two perspectives is extremely important, since the all-sky camera captured intense coronas and overhead structures, while the north-facing camera was able to record bright pulsations and more fine detail structures to the north. Also, the camera live streams were extremely popular that night, with over 35,000 live stream playbacks over just 10 hours. That's an increase from 1,300 viewers during the storms on October 11th and 12th. The impact of NoDDAC in aurora chasing communities cannot be overstated. The summer months in 2021 were relatively quiet for auroras, but the north-facing camera on NoDDAC was able to capture noctilucent clouds on the night of June 14th, 2021, shortly after sunset. These findings mean NoDDAC is not only useful for scientists studying aurora, but those studying noctilucent clouds as well. In the future, we plan to make NoDDAC data more accessible by introducing a user-friendly website and interface. We are also open to collaborations between other relevant citizen science projects and any other scientific efforts that could make use of NoDDAC data. Lastly, we are always trying to increase NoDDAC's impact both in the public and scientific spheres, so if you have any feedback, please let us know. Their first year of NoDDAC has made us realize the capabilities of the project and gives us motivation to keep improving. We are excited to share these data with you today, and thank you for your time listening to this presentation. Thanks.